So let me introduce. Greetings. Let me extend a warm virtual welcome to the NYU Tandon School of Engineering and the latest seminar in what has proven to be an important and informative series aimed at unifying scientific communities around the influential research ideas of today that we predict will have major impact tomorrow. AI is already recognized as an important topic of research with applications in medicine, biology, neuroscience, and other vital fields. And we hope that the scientific discussions that result here will contribute to building a better world and promote groundbreaking discoveries. I would like to thank Dean Jelena Kovacevic for her strong support, as well as my own Department of Electrical and Computer Engineering for hosting this series, which is evolving into quite a significant event in the AI world. When I first conceived of the idea, I hoped that I would be able to attract highly esteemed speakers doing revolutionary work in their respective fields. I say with some humility that I succeeded to an extent that I never even imagined. Our guest today is the most recent example. Nicolò Cesa-Bianchi is a professor of computer science at the University of Milan. Nicolò Cesa-Bianchi is professor of computer science at the University of Milan in Italy, where he leads the Laboratory of Artificial Intelligence and Learning Algorithms. He holds a joint appointment at the Polytechnic University of Milan. His research focuses on the design and analysis of machine learning algorithms for online learning, sequential decision-making, and graph analytics. He has served as president of the Association for Computational Learning and co-chaired the program committees of some of the most important machine learning conferences in the world. His many laureates include a Google Research Award, a Xerox Foundation Award, a Criteo Faculty Award, a Google Focus Award, and an IBM Research Award. And he is a fellow of the European Lab for Learning and Intelligence Systems, known as ELLIS, a member of the organization's board, and the co-director of the Milan ELLIS unit. Nicolò is the co-author of the highly regarded monographs, Regret Analysis of Stochastic and Nonstochastic Multi-on Bandit Problems, and Prediction Learning and Games. And proving that he has a wicked sense of humor, he has referred to the latter as Perdition, Burning, and Flames, a hell of a book. His presentation is titled Online Learning, Bandits, and Digital Markets, and in it, he will be tracing the roots and the main algorithmic ideas behind online learning, a topic of great interest, particularly to those of us in academia, and showing how solving problems arising from digital markets has improved our understanding of what machine learning algorithms can do. So without further ado, I give you Nicolò Cesa-Bianchi.
Thanks a lot, Anna, for your introduction. We did try very hard over the last 3 years for me to come in person, but we eventually decided it was just a good idea to give the talk online, and maybe to but I'd be very happy to come over and visit on some other occasion in the future. So
we'll be very happy to have you in person.
Thank you. Let me share screen. Okay, and then just a second. Okay, good. So yeah. So this talk is about online learning and application to digital markets, which is a kind of a playground, very exciting for this kind of technologies. So let me start with something different, because it's useful for people, especially for people who are not familiar with online learning. It's useful to introduce a different paradigm in machine learning, which is the statistical learning. And it somehow is considered as the main reference framework for the mathematical analysis of machine learning. But unlike physics, there's not only a single standard model in machine learning, but there are competing paradigms, or maybe not competing, but different viewpoints on the same problem. So statistical learning, the founding fathers, there's Vladimir Vapnik, who characterize learnability in terms of sample size, how much information we should, it's necessarily sufficient in order to learn something from a statistical sample. And Leslie Valiant provided the characterization of the computational complexity of learning problems. So this is an area that I'm sure many of you know well, and provided amazing contributions to our understanding of machine learning, including guidelines to practitioners, but also algorithms that are both very effective in practice and are principled. They have theoretical performance guarantees. Okay, so in statistical learning, one of the cornerstones is the bias-variance decomposition. You can basically use the notion of statistical risk to rank how good is an algorithm with respect to a learning problem characterized by some loss function and some data distribution. And you can define a notion of optimality, very crisp, which is Bayes' optimal predictor. And the bias-variance decomposition will tell you that if you give a training set to a learning algorithm, this algorithm will output some predictor, and the risk, the statistical risk of this predictor can be viewed as the combination, the sum of the variance error and the bias error, plus the residual term, which is Bayes risk, which is unavoidable. So this is a very, as I said, a very nice and successful paradigm. You can really understand and trade off the overfitting and underfitting in machine learning. However, there are scenarios like scenarios in which your data comes in a stream, for instance, because you have financial markets, you have sensors, or you have users who interact with websites. All these scenarios provide data streams that are a different setting with respect to the setting that is usually taught or the reference setting for statistical learning. Indeed, when you have a data stream, you can update your learning model as soon as new data arrive. And this is not really fitting the train test paradigm of statistical learning. So that's why people, I would say, simultaneously were looking at learning paradigms that were a little bit different from the traditional statistical learning paradigm. So online learning is actually something that is, comes a long way, is connected to the theory of repeated game, which was pioneered in the 50s by James Hannan and David Blackwell, the first two pictures that you see up there. And even early analysis of machine learning, like the analysis of the number of mistakes or the perception convergence theorem by Bloch and Novikov in the 60s, were essentially online learning analysis. And later, especially in computer science, there was a sort of a formalization of the online learning model, especially due to Nick Littlestone, the guy with the straw hat in the middle, and Manfred Warmuth. At the end of the 80s, with the PhD thesis of Nick Littlestone, there was this, I would say, a first formalization of what is now called online learning. And in the Soviet Union, Volodya Vovk independently developed a similar online learning framework with the paper aggregating strategies that is, you see almost the same year. And however, many similar ideas were emerging in areas like information theory and statistics and game theory. Okay, so it's really a simultaneous evolution of ideas in similar fields that were later connected. Right, so let's talk a little bit about an informal view of the online learning protocol. So we have some algorithm that will start with a default model. By model, I mean a predictor which maps data points to predictions. And there's going to be a stream of data, and for each new data point in the stream, the current model will be tested on the next data point of the stream. And the algorithm will be charged with some corresponding loss. So the loss of the current model on the next data point in the stream. And this can be any loss of our favorite loss, like square loss, classification loss, log loss, or any other loss that you're interested in. And then, given this new piece of information, the algorithm will compute a new model, will make a model update. The main idea is that the computation of the new model should rely on local information, by which I mean the current model and the next data point. So in general, I shouldn't be remembering the entire past sequence of data points in the stream, because otherwise it would defy the whole idea of online learning. Okay, so as I said, that there is a natural application of this paradigm, this learning paradigm in data streams. However, oh, sorry, I was forgetting. Yeah. So one key aspect of online learning is that typically there are no assumptions made on the mechanism generating the data stream. And this is where you can see the game theoretic root. So in some sense, you may imagine as if there was nature or an adversary that is actually generating a data stream that I'm hearing some background noise. Someone has the mic on. And right, so nature or an adversary might be constructing a stream of data that is trying to make you suffer a loss as high as possible. So in this case, we really give up on any statistical assumption on the data stream. Right, as I said, you can definitely apply this mechanism, this paradigm in other contexts like stochastic optimization. Just because your data set is so huge that you can only use local optimization techniques in order to minimize training error, for instance. So in that case, you create a stream artificially by sampling stochastically from the training set. And now the stream will correspond to this random sequence of data points. But then you can apply any online learning algorithm by pretending that this is an arbitrary data stream. Okay, so now let's be a little bit more formal, and let's introduce the main formal framework, which is online convex optimization. And this is the framework within which algorithms are typically, online learning algorithms are typically designed and analyzed. So we have a model space, which is some convex closed and non-empty subset on R of R to the D. And typically, our models will be parameterized, will be parametric models typically, and will be parameterized by a vector of D reals. And for instance, you can think of like a linear regression example, right? And okay, so instead of thinking of a stream of data points, we think of a stream of loss functions that are convex. So in other terms, the data point is absorbed into the loss and becomes becomes an index in the loss function. So now you are facing a sequence of convex losses that you can think of them as your favorite loss applied to a sequence of data points. Okay, but this could be also a more general setting, as long as your functions are convex. So now, as this sequence of loss functions unfolds over time, you're going to test your current model on the next loss. The algorithm will be charged the corresponding loss, and then we'll be updating the model based on the previous model and the feedback information, which will reveal information about the loss function, the current loss function, for typically some information that we can have access to is through a first order oracle. So typically, we might have access to the gradient of the loss on the current model. Okay, If you have any questions about this, please. Okay, let me just open the chat. Maybe. All right. Okay. Right. So now the idea here is, okay, how are we going to measure the performance of a learning algorithm in this online learning paradigm, right? So in statistical learning, we have a notion of statistical risk, which is pretty well defined. We have a data distribution, and we can measure the statistical risk of any predictor with respect to the data distribution and the loss. Here in online learning, we replace the statistical risk with sequential risk, and sequential risk is just what you see there. So is the loss, the cumulative loss of the sequence of models that have been generated by the algorithm over the sequence of convex losses that represents the stream. Okay, so unlike statistical risk, here the sequential risk is defined with respect to a sequence of models that are the models generated by the algorithm and by a sequence of losses. We cannot take expectations because there's no randomness, right? The environment is completely deterministic. So in statistical learning, we used to look at the variance error, which is the difference between the statistical risk of the model generated by the algorithm and the statistical risk of the best model in the class of models that are accessible by the algorithm. And here we define a similar notion, which is called regret, which is just the difference between the statistical risk of the sequence of models generated by the algorithm and the sequential risk of the sequence of models generated by the algorithm and the sequential risk of the best model in the model class. Okay. So you see that there is a slight asymmetry here because whereas the algorithm is able to change its model at every time step, the comparator here on the right-hand side is comparing a single best model against the same sequence of losses. However, on the other hand, again, we have no statistical assumptions, so it's a completely adversarial sequence of losses that the algorithm is going to be facing. And so this definition of regret makes sense exactly because we are not using any stochastic source of data. Okay, so the main question that online learning is facing is, can we ensure that our regret is vanishing on average when divided by time for any sequence of convex losses, maybe with some additional assumptions like Lipschitzness. Okay, this corresponds to asking that our variance error vanishes as my sample size grows to infinity. Okay, and vanishing regret will be the equivalent of vanishing variance error. Okay, so one of the main ideas, so if you want to go and solve this problem, you can start again and take inspiration from statistical learning. And one of the main, the most obvious techniques in statistical learning is empirical risk minimization. I want to take the model that within the class of models that I have access to minimizes the training error. In learning, in online learning, this would respond to minimization of sequential risk. Okay, given a prefix of my loss sequence up to time t, I want to take the model that minimizes the sequential risk. Yeah, doesn't sound really exciting because it's not online, right? You have to remember all past losses in order to be able to perform this minimization. So it's hardly possible to call this an online learning algorithm, but we will see soon that we can fix this problem in a very elegant manner. All right, so this algorithm is simple. It's kind of disappointing because it's an online, and it can be really badly fooled when losses lack curvature. And you can view this as a sort of an online overfitting phenomenon. And by fooled, I mean that the regret will grow linearly with time, okay, which is as bad as possible. So basically, random prediction we do just as good if with respect to sequential risk minimization. Whenever the losses lack curvature, but we know that there are very interesting losses like hinge loss who lack curvature. Okay, so this is the problem. And the idea is that we artificially inject curvature by using a strongly convex regularizer. So instead of minimizing sequential risk, we minimize a regularized version of sequential risk. Okay, now, yeah, this strongly convex regularizer is going to change, is going to introduce some bias in a sense, and it's going to change a little bit the problem that we're solving. So how is this going to affect things? So first of all, we do something that is simple, but very effective. So since losses are convex and all we care is regret, which is a difference of losses, we can replace loss by loss gradients and essentially minimize an upper bound on the regret. So if we pretend that our true losses are actually the gradients of the actual losses, we try to minimize regret with respect to the loss gradients, we are just minimizing an upper bound on the regret. And it turns out that we don't lose much by doing that. So we now look at the same problem as before, but we just replace loss with loss gradients, right? And then we can, since we have now a linear problem, we can just accumulate the gradients, the sum of the gradients in a variable, and look at this problem over here. Okay, now we have a convex constrained problem. There is a strongly convex part, which is a regularizer, and there's a linear part, which is our learning parameter W and the accumulated gradient. Okay, so what we do, we observe that because of the nature of this convex optimization, which has a strongly convex part and a linear part, we can see that the gradient of the convex conjugate of our regularizer is the solution of the unconstrained minimization problem. And by unconstrained, I mean that I replaced my model class W with the entire IRD. Okay, this is really cool because it somehow avoids in an elegant way the problem of remembering past information. The entire past information is stored in the state variable, which is just the sum of the gradients. And then I can phrase the algorithm in a very simple way. And this is the follow the regularized leader algorithm for online learning with linearized losses. So first of all, I'm at every time step, in order to update my model, I first have a gradient update in which I update my state variable by adding the new gradient, which the Oracle gave me as feedback. Then I do this mirror mapping, which amounts to solving the unconstrained minimization problem. And then I do a projection onto the onto my model class V, and the projection has to be done according to the geometry induced by the regularizer, which corresponds to a Bregman divergence. And this thing can be computed easily for many kind of regularizers, and there are lots of books about convex optimization, which will tell you how to perform these projections. Okay, so we have now a nice and effective algorithm. So we want to see the regret, and the regret bound is very simple, elegant, and general. So the regret after time t for any stream of Lipschitz, uniformly Lipschitz convex losses in a model set whose diameter is d squared, defined in that way, is bounded by 2LD square root of t. So this means that my average regret is vanishing at rate 1 over square root of t. And this bound is up to constants for any regularizer, which is a squared norm, and also for other regularizers like entropic regularizer. So it's a general, simple, and tight bound that accommodates any sequence of convex Lipschitz losses and any choice of the regularizers. So there is a very rich literature that tells you how to choose regularizers, but we want to see now how can we apply these ideas to solve problems that are where the feedback is partial. And this is the so-called Bandit model, which is a variant of the online learning framework. So in Bandits, it's a very special case of online learning in which we have k actions. So you can think of them as the coordinates in the d coordinates in our previous online learning setting. And there is the stream of losses. You can view it as an unknown deterministic assignment of losses to individual actions. So k actions, at every time step, every action has some loss, and this loss is an unknown number between 0 and 1. Okay. And now the algorithm in every time step will choose some action. It's a sequential decision-making problem. So the algorithm will pick an action, possibly using randomization, will incur the corresponding loss component, and will observe the loss incurred. So we'll just observe the component of the loss corresponding to the action chosen. If you think of this as a linear loss, this means that you are not observing the entire gradient of the loss, but you're only observing the gradient component corresponding to the coordinate that you picked. Okay, so this is a nice framework that has very many applications in recommender systems or online advertising, dynamic content optimization, clinical trials, so on and so forth. In clinical trials, for instance, you have a choice of k treatments, you have a sequence of patients, and you are choosing for every patient a possibly different treatment, and then you observe the effect of that treatment on that patient, which would be like observing the loss component of the action you chose at that specific time step. And the entire idea here is, again, that we make no assumption on the way this sequence of losses has been generated. So everything is completely deterministic and potentially adversarial. Okay, so now, since everything, the losses are linear, the regret can be equivalently defined in the following way. So I have the regret of a player that chooses a sequence of actions is measured against the single best action. And the single best action is because essentially you are minimizing a linear loss over the simplex. So the minimizer will be always a convex of a corner of the simplex. That's why the minimum of your linear losses will always be found on a specific action, on an individual action. All right. And the expectation you see here, it is because we will typically consider randomized player. So the choice of the actions I1, I2, I3 will be randomized. All right. So now one algorithm that is often used is the XP3 algorithm, which corresponds to using the follow the regularized leader with an entropic regularizer. And we're going to use randomized loss estimates. Why do we use randomized loss estimates? Because we are not observing the entire gradient of the loss, but we only observing one component of the gradient of the loss at every time step. Or if you like, we are only observing the loss of the action we chose. We never know the loss of the actions we didn't choose. Okay. So now it turns out that you can prove an upper bound. I hope you can see my cursor here. You can prove an upper bound on the regret, which look like this. Okay, let's spend a little bit of time, just a few seconds. So eta is a learning rate, k is the number of actions, t is time, and this L hat is our randomized loss estimate when randomization is just internal to the algorithm. So this is a notion of variance. And the entire idea of the bandit analysis is to control this variance in a nice way. And basically, this variance can be controlled, can be upper bounded by k. And by choosing the learning rate properly, we get this bound over here on the regret, which looks similar to what we had. You still see the square root of t dependence. And you can shave off the logarithmic factor over here by using a slightly different regularizer. And then you get the bound on the regret, which is tied up to constant. Okay, so this is the basic how we can use our online learning technology and follow the regularized leader in a setting in which, and combine it with randomized loss estimates and we get bounds that look very much like those we used to get before, even though we have a partial feedback. Now, let's look at a few applications of this in online markets. So online markets, the idea is that you have a high volume stream of trades where both buyers and sellers are algorithms. Decisions are typically prices, and in order to abstract away the granularity of the prices, we will typically consider a continuous and bounded price range. So we assume that prices are real numbers. And the idea is to maximize the revenue, or either buyer or seller, in a sequence of trades, which corresponds in our in our lingo to minimize regret with respect to the revenue of the best fixed price over the same sequence of trades. Now the sequence of trades is our stream, and we want to minimize regret with respect to the best fixed price, which is the best fixed action for that sequence of trades. All right. And the main theme that we will explore here is that to exploit the structure of the feedback that we get, which is specific to the market problem, in order to control the variance of our revenue estimates. Now losses become losses become revenues, but the same idea, the ideas are the same because everything is bounded. So you can think of a loss as 1 minus a revenue and vice versa, and things are completely the same. All right. So there's been a number of applications. This is just a few applications that I would like to focus on for the rest of the talk. And each one of these applications will, will exploit a different feature of the problem in order to get the best possible control on the variance of revenue estimates. And this is how we will be able to use our Bandit technology as best as possible for these problems. So the first problem is posted price options. So at every 10 steps, there's a buyer who arrives to buy a t-shirt from you, and the buyer will have some private valuation for your t-shirt, and you will set a price because you're doing dynamic pricing, and without knowing the buyer's valuation, will you set a price for your t-shirt. And if the price is smaller than the buyer's valuation, then you will sell it at that price. Otherwise, the buyer walks away and your revenue is zero. And your feedback is going to be yes if you sell this item, otherwise no. So you only see whether the items get sold or not, but you never get to see. You can compute your own revenue function, which is just the price that you posted if you sold it, and zero otherwise, and that you know. But you never observe the evaluation of the buyer, which remains completely unknown. So now the regret is defined in similarly as before. It's just the other way around. So because we are looking at revenues instead of losses. So we are looking at the best price in the model space, which is this decision space, which is the unit interval, and the one that maximizing the cumulative revenue. And then you're looking at the difference between the cumulative revenue of the best price minus the cumulative revenue of the sequence of price that have been posted by the seller, which is running your Bandit algorithm. Okay, so you want to control this thing over here, and you want to prove a sublinear bound, possibly order of a square root of t, as we were able to do before. So first thing you may observe that in posted price, you see the revenue function over there as a function of VT, which is the unknown parameter, and the P, the price, the posted price P. This function in Lipschitz from left to right, okay, it satisfies that condition. So this allows you to discretize prices while controlling the approximation error. So what do I mean by that? I mean that I can look at the grid over the prices at the grid size epsilon. I can now decompose regret into some bandit error over the discretized grid of prices, plus some approximation error, which is the error I incur because I discretized. So this is the bandit error, which is just regret over the discretized set of prices, and this is the approximation error, which is how much, you know, how much do I lose because I am looking not at the best price, but the best discretized price. Okay, now one side the Lipschitz net is going to take care of the approximation error. I'm going to pay at most epsilon at every time step. So over time, over capital T time steps, I'm going to pay at most epsilon capital T. Then I can run my XP3 algorithm over the discretized set of actions. And, you know, as before, the variance of my revenue estimates will be bounded by K, because this is what I told you, you can do in the bandit analysis. Therefore, the final bound will be just the final bound of the regret will be just the sum of approximation error and the bandit error. And by choosing K is order of 1 over epsilon. So by tuning epsilon, I'll be able to achieve a T to the 2/3 bound on the regret, which is tied up to logarithmic factors. So this is not improvable. If this is up to logarithmic factor, this is exploiting optimally the information, all the information I have. So let's see now if I can do any better by looking at problems which have a different feedback structure. So the idea is to look at the second price auctions with reserve price. And this works. This is what you know, large ad exchanges have been using until not so long ago. Now everybody switched to first price. Anyways, second price auctions with reserve price. You have a seller that the seller will choose a reserve price for the item, and simultaneously bids will be submitted. If the highest bid is below the reserve price, and then you're not selling. Otherwise, the winning bidder will pay the maximum between the second highest bid and the reserve price. So your revenue function as the function of the reserve price will be something like that, where B1 is the winning bid and B2 is the second highest bid. Okay, so this is something that you're looking at. However, this time we can assume that the feedback will be not only the revenue, but also the winning bid, because typically ad exchanges will give you the winning bid, will give back to the seller the winning bid as a feedback information. So we can observe that these two pieces of information allow us to compute the revenue of any reserve price above the one that we actually played. So every time step we play some reserve price PT, but we can compute the revenue because we have these two pieces of information. We can compute the revenue of any larger reserve price that we could have played. So we get a bit more of feedback as opposed to the one we get in the bandit case, where you only get to see the revenue of the price you played. Here you get to see the revenue also of prices that you didn't play. So now we can use this feature to gain a better control of the variance. So we proceed as before. We discretize prices. We decompose regret into bandit error plus approximation error. We use one-sided Lipschitz to control the approximation error. And now we run XP3 over these prices, the discretized prices, but we will add a small probability of using a zero reserve. Using a zero reserve price means essentially that we can reconstruct the entire vector of losses for all possible reserve prices, because as I told you before, we can compute the revenue of all reserve price is larger than the one we played. So if we play 0, we can reconstruct the revenue of any reserve price. So with small probability, we play this revealing action. So we play a 0 reserve. This is costing us because a 0 reserve doesn't allow us to win, to get a revenue, but we get a lot of information. And using this additional information, we are able to get a better control on the variance of our revenue estimates, a logarithmic control instead of a linear control. And the logarithmic will be based on this reciprocal this probability. Now we can combine the approximation error and the bandit error with this refined variance bound, variance control, and we get to see that we can improve and get a regret bound, which scales again with the square root of t times a logarithmic term. So we are doing better than we did in the dynamic pricing case, where we could only just use the bandit out of the box, but we didn't have any way of getting an additional control over the variance. All right, now let's see a different problem. And this problem, we call it adaptive taxation. So here, again, a buyer arrives. He has some private evaluation for the tax rate. So he's saying, okay, the seller is the policymaker will set the tax rate dynamically, and you know, the buyer may decide if the tax rate is too high for their purchase, he would walk away. And so if VT is more than PT, then item is sold, and the feedback will be as before, the item is sold yes and no otherwise. So what is the revenue here? So we're looking at two kinds of revenue. One is the public revenue. So it's the tax rate that we get, and this goes to the, you know, as public welfare. But also there's a buyer's private welfare, because the buyer saved money if the tax rate was smaller than they thought, than their, you know, private value. And however, this piece of revenue is unobserved because we never observe VT. Okay. So now we want to measure regret against with respect to social welfare, which will be the sum, the weighted sum of public revenue and private welfare. The trick here is the following. Okay, so first of all, the curve looks very similar to dynamic pricing, although the straight line doesn't start from 0 because we have this this part here, which we don't know about because we don't know VT. So, however, as you can see, this is Lipschitz from left to right. And the other thing we may observe that the public revenue is the same as posted price. So we cannot hope to get a regret any better than t to the 2/3 because this was already the lower bound that we had on posted price. Okay. And as we said, that this private welfare component will depend on the unknown t, which means that I cannot observe my revenue because I'm missing VT. So I cannot compute the private part of the revenue, right? All right, so we proceed as before. We can control, since the thing is Lipschitz, we can control approximation error. However, in order to estimate the private part of the welfare, what we do is that occasionally we set a random tax rate with small probability. So this is the equivalent in this problem of playing a 0 reserve price with some small probability. Here we set a random tax rate, and by setting the random tax rate, we are able to construct an estimate for the private welfare part of the revenue. And this is the estimate. And we don't see VT, but we know whether we are above or below VT because we see whether the item gets sold or not. And in expectation, with respect to the random draw of this uniform random variable, we have that we have the correct estimator. We have the expected value of this estimator. It will be the private welfare. Okay, so now we can do discretization. We can have an estimate of the private welfare. We have an estimate for the other part, which was similar to posted price. And if we combine the variances of these two estimates, we get something similar to posted price. This is so will be the posted price component, and this is the component that I get because I'm estimating the private part of the revenue. And by choosing again the parameters, I can get a final bound, which is on the regret, which is t to the 2/3, which is again best possible because, as I said, just because this problem is more complex than posted price, I cannot get any better than t to the 2/3. All right. So now let me move to the last problem, which is bilateral trading. And this is like what you do when you call Uber. So basically, there's a seller and a buyer. Some driver is selling a ride, and you want to buy a ride, and you have the seller has some smallest amount that he is gonna be willing to sell the ride for, and you have the largest amount that you're willing to buy the ride for, and these are private values. So the platform will post a price both to seller and buyer, and if the price is in between, then the trade will happen because everybody's happy. And the feedback to the platform will be yes if the ride took place, or no otherwise because either one of the two walked away. So we can now compute the revenue. The revenue is the social welfare, if you like. It's just the sum of the buyer's net gain and the seller's net gain times the indicator function that the trade happened. And this corresponds to that, which is this revenue function over here as a function of the posted price for the platform. And this is bad because we cannot observe the revenue. We just know whether the trade happened or not. So we cannot compute this difference over here. We don't know what were the parameters, the private values for seller and buyer. And this thing is not Lipschitz at all, as you can see, not even on one-sided. And therefore, you can construct essentially a lower bound in which you can make you can make any algorithm to look for the best price, P star, which will be some real number, but any price that is posted which is away from this real P star, with this hidden P star, will cause you a constant regret, which means that your regret will be linear in time. So you're hopeless. So what can you do here? And I'm almost done. What you can do is to use a trick that has been used a lot in the analysis of algorithms. So you can move from worst case analysis to smoothed analysis. So we do this in two following steps. So first of all, we have two problems here. The two problems are that we don't observe the revenue and the function is not Lipschitz. So we address these two problems using two different tricks. So first of all, we will assume that the platform is allowed to post a different price to the seller and to the buyer. These two prices will be always in this order, and the trade will happen again if everybody is happy. So if the seller is happy and the buyer is happy, because they're getting the prices that are at least as large as at least as small. And the feedback will be again yes if the trade happened and no otherwise. And this is going to be your regret, which now depends on your revenue, sorry, which now depends on the two prices. And you notice that actually, if you want to maximize this as a function of P and Q, you will choose P equals Q. So posting two prices is not good, doesn't get you a higher revenue, it only gets you more information because you can post two things instead of one. Okay. So, however, the feedback is the same. You just get one bit of feedback. However, this additional power, this additional exploration power will allow you to estimate the revenue. It remains the problem that your function is not Lipschitz, and now you're using a smoothed analysis in order to address this problem. In other words, you are assuming that at each round, the seller and the buyer evaluations are not deterministically chosen by an adversary, but they're jointly drawn from a distribution which is chosen by the adversary. So in other words, the adversary can choose a distribution, but then cannot control the draw of the buyer evaluation, seller and buyer evaluation from this distribution. And distribution has to be not too far from the uniform distribution. Okay. Right. So in other words, this allows you to prove that the revenue becomes Lipschitz once you impose these smooth constraints on the adversary. And now you can discretize, and you can use the two prices to provide a randomized revenue estimate for your revenue. And by putting the two things together, you can prove a bound on the regret, which has this weird form. And see, this rate is different from all those that we saw before. We saw square root, we saw t to the 2/3, and this is t to the 3/4. Is this any real, or is it just an artifact of our analysis? Because now our analysis has many moving parts. But we can prove that actually this bound is tight up to log factors, even when the platform is giving the stronger feedback whether each of buyer and seller accepted the deal or not. So 2 bits instead of 1 bit. Okay, so this was my last example. And yeah, so what are the main take-home messages here that I would like you to take home? So yeah, online learning is cool, is a very algorithmic machine learning framework and non-statistical, and provides a new perspective on the design of digital markets, which is something interesting in its own. And the bandit analysis allows us to capture really how the quality and the quantity of the feedback will affect the learning rates, the regret. And we can do this up to a very fine detail, up to logarithmic factors or up to constants in certain cases. And yeah, it's very interesting. You know, it's going to be very interesting for us to move on with these studies and look at entire ecosystems of many users with different incentives interacting through learning agents, because this is how, you know, the digital markets look like. We have different actors, different users. Everybody has different utility functions, but they will deploy agents that are actually learning algorithms, and these agents will interact with each other. And we want to understand what are the equilibria, the properties of these dynamics, and how the users can steer these dynamics by providing, by parameterizing the learning agents in a way that might be not fruitful with respect to their own incentives. Okay, that was it. And thanks a lot. I hope you enjoyed the talk.
Thank you so much, Nicolò. Thank you so much. So maybe a warm-up question regarding the conclusions slides. So you're talking about generalizing this framework to more complicated ecosystems where you're learning with agents. Can you comment on how the analysis can be potentially extended to that? What are the technical tools that?
Yes, absolutely. So this will be another very nice talk, maybe next time when I come in person. So as I told you, one of the stronger roots of online learning is in repeated gains. And so people since the early 80s looked at the equilibria of regret minimization. Okay, so what is pretty well understood is, okay, if you have regret minimizing algorithms that play together, what are the equilibria that this regret minimizing algorithm will converge to? And there are notions, there are variants of regret, which allow you to converge to equilibria, which are supersets of Nash. So typically you have a correlated or coarse correlated equilibria. However, this is different if you think that actually these learning algorithms are, you know, agents acting on behalf of users. Users might decide, you know, to program these learning algorithms in a way that, you know, advantages for them against the others. So now the real game is between the user